Great. So thank you, Dr. Melosso, for being here. We're delighted to have you today.
Thank you very much, Heather. So, okay, hi everyone. I'm Mattia Melosso from Italy, and this is my brief talk about the first laboratory and interstellar detection of zeta 12 etendiol. In the context of the RNA world hypothesis, so it's assumed that RNA represents the first self-replicating chemical unit, and thus played a major role in the origin of life on primordial Earth. So although this hypothesis is quite accepted, it is still debated how RNA units could have formed under the physical-chemical condition of early Earth. One of the most comprehensive route has been introduced recently by Becker and co-workers for explaining the simultaneous formation of pyrimidine and purine nucleotides. So here the key ingredients for RNA are small molecules that were plausibly available on prebiotic Earth, such urea, cyanacetylene, or let's say HCN or hydroxylamine. The formation route of purine and pyrimidine nucleotides are different, but in both cases, so they share the need of ribose as reactant, since ribose is an essential building block for constituting the RNA unit. On the other hand, ribose is believed to come from the so-called Formose reaction. So this is a process that uses formaldehyde as the starting material and proceed through aldol, reverse aldol, and isomerization reactions, thus forming a great number of 4, 5, and 6 carbon atoms sugar, including ribose. However, this type of reaction exhibits many limits in aqueous media. So it's possible for sugar formation early Earth is quite reduced. But on the other hand, it's more conceivable that Formose-like reaction might have played an important role in the gas phase chemistry or dust grain chemistry occurring in the interstellar medium, and that molecules formed in that medium could have then been transferred to early Earth by meteoritic or cometary bombardment. And this hypothesis is of course supported by the detection of interstellar molecules such as formaldehyde and glycolaldehyde, which are the two simplest species occurring in this route. But more complex molecules of the Formose reaction remain elusive so far. Here, however, an highly reactive intermediate that promotes the transformation of glycolaldehyde to glyceraldehyde is represented by etendiol. And also etendiol is really interesting because it then forms glyceraldehyde, which is the most simple sugar that we can find in nature. But to date, etendiol is not a known interstellar molecules, but mainly because there were no spectroscopic information available to do that. This molecule, etendiol, also belongs to the family of C2H4O2 isomeric family, which is well represented in the interstellar medium. In fact, 3 out of 5 molecules, so namely acetic acid, methylformate, and glycolaldehyde, were already detected in space, while the 2 undetected molecules that are 1,1 and 1,2 etendiol, they cannot simply be searched at all because there is a great lack of spectroscopic information for these 2 species. In fact, laboratory studies of etendiol were limited to date to the condensate phase and to spectral region or techniques that are not so useful for astrochemists. So we wanted to fill this gap, and in this work, in this project, in order to enable the interstellar identification of 1,2 etendiol, which in turn would shed light on the possible formation of sugar in space, we aimed at a spectroscopic characterization of this species by means of rotational spectroscopy. So first we had to explore these species by computational methods. So we want to investigate the potential energy surface for this system in order to locate the most stable conformers of the species and consequently the spectroscopic parameters relevant to our study. We then have optimized the production of these unstable species, which cannot be purchased commercially. So we aim it at the production of these species by means of flash vacuum pyrolysis, and then we recorded the spectrum up to 375 gigahertz. And finally, once the spectrum was analyzed and the spectroscopic constants obtained, we used them to prepare some spectral line catalogs to be used for the subsequent search of ethandiol in the giant molecular cloud G+0.693, which is a very chemically rich source located in our galactic center. So the exploration of the potential energy surface was initially carried out with the density functional theory, in particular using the B2LYP method in conjunction with an augmented triple zeta quality basis set. And in particular, we scanned the portion of the path along the two dihedral angles involved in the OH bonds. And this scan revealed the existence of a few stationary points. And in particular, we were able to locate two minima on this path. So minimum 1 represents the global minimum and was assumed as our zero reference energy, while minimum 2 is the second most stable minimum. So it's the second most stable conformers, but it's already 15 kilojoule per mole higher in energy than minimum 1. Moreover, the paths contain two saddle points. We have TS1, which is the transition state that connects two equivalent configuration of minimum 1 with a barrier of about 10 kilojoule per mole, while TS2, instead is the transition state ruling the isomerization between minimum 1 and minimum 2. But because the minimum 2 is too high in energy to be observed in our experiment, we only characterized a minimum 1 at a higher level of theory. So we retrieved accurate values of the rotational constants of minimum 1 by employing the so-called CBS plus CB composite scheme, whereas the vibrational contribution and the estimate of the centrifugal distortion terms were carried out, were computed using the MP2 method. In the same time, we had to test an efficient production method of ethandiol by flash vacuum pyrolysis. So we tested this process by recording by monitoring the NMR spectra of the pyrolysis mixture. And we used as precursor species the bis-XO5 norbornene 2,3 diol, which at a high temperature undergoes a reverse Diels-Alder reaction, and thereby breaking into fragments, which are cyclopentadiene and the zeta form of 1,2-ethandiol. Actually, some amount of ethandiol tautomerized to the most stable enol form, which is glycolaldehyde. So glycolaldehyde is also observable in the spectrum. But in any case, the proton and carbon-13 NMR spectra revealed good signals, which are here marked with the stars, that are consistent with the formation of ethandiol. So at this point, everything was ready for starting the experiment. And the measurements of the rotational transition have been performed between 75 and 375 gigahertz using the frequency modulation spectrometer located at the University of Bologna. In this spectrometer, the main source of radiation is a GaN diode, which is driven by a centimeter wave synthesizer. And the frequency and phase stability of the GaN diode is ensured by a phase lock loop, whereas the overall frequency accuracy of the spectrum is provided by a rubidium atomic clock. As I said, ethandiol was produced by flowing the precursor vapor, which is the norbornene diol, through a quartz tube, which is surrounded and heated by an oven set at the temperature of 750 Celsius degree before entering the absorption cell. And then the the output radiation. So the radiation absorbed by a tendiol is detected by a liquid helium-cooled bolometer, and then the signal is processed by a lock-in amplifier, which is set at twice the modulation frequency employed. The spectrum recorded during the pyrolysis showed the absorption due, of course, to the byproducts, cyclopentadiene, which is shown in green, and glycolaldehyde shown in blue. But the most intense feature detected in the black spectrum that you see at the center of this figure do not belong to any of these two species, while they match pretty well the spectral patterns predicted for zeta-1,2 etendiol in orange. The first assignment, which is shifted by around 0.2% in frequency with respect to the theoretical estimate, has then been used to refine our spectral prediction in order to reduce the discrepancy between the computer and observed spectra, and to facilitate the search and interpretation of the subsequent measurements. We at the end, we measured as much transition as possible in the frequency range up to 375 gigahertz, and we determined an extended set of spectroscopic parameters, which compare very well, I would say, with those computed previously. We recorded and analyzed both A and B type transition, but we failed to observe any C type transition, even though we predicted an equilibrium structure of a tendiol as non-planar. So in principle, all the three components should be observable. And this was a little bit puzzling at the beginning, but the experimental evidence is then justified by the very low barrier to planarity, which is computed as 0.2 kilojoule per mole. So because there is only a motion of a single H atoms that rule the barrier to planarity. So as a consequence, even if the symmetry of the molecule is predicted to be C1 at equilibrium, then in the ground vibrational state, the molecule is effectively planar, as can be confirmed by the very low inertial effect. And this is why we couldn't observe any C-type transition. But in addition, we observed some splitting in most of the absorption feature of the spectrum. And these splitting are a clear evidence of a tunneling motion that exchanges the two OH group within the molecular frame, as we expect by the moderate barrier that separate the two equivalent conformation of minimum 1 and the transition state 1. And the relative intensity of each pair of transition is 10 to 6 in agreement with the spin statistics governed by the exchange of two pairs of hydrogen nuclei. So thanks to the analysis of the rotation inversion spectrum, we were also able to determine the energy difference between the two inversion states, and also the correlative terms that govern the interaction between these two states. So as a final step, based on our spectroscopy, we have prepared a spectral line catalog to be used for searching zeta-1,2 etendiol towards the molecular cloud G plus 0.693. Differently from the nearby Sagittarius B2 region, no evidence of star formation were observed in this source. So molecules that populate this source are found to have very low excitation temperatures in the range of 5 to 20 K. And this low temperature represents a great advantage for the discovery of new interstellar species, because only the low energetic states are populated. There are no vibrationally excited states, so we are not that close to the confusion line limits. And moreover, this cloud exhibits a very rich chemical complexity and diversity, as demonstrated by several interstellar complex organic molecules detected here for the first time in the last few years. So this represented the ideal target for our search. By using the spectral line survey recorded with both the IEBES and IRAM telescopes, in Spain, we have searched for and successfully identified a tendiol emission toward this source. So we detected 9 pairs of unblended or partially blended transition between 35 and 95 gigahertz with an average good signal to noise ratio. The analysis of the emission spectrum was performed assuming a local thermal equilibrium condition. So, and this allowed us to retrieve, to derive an ethendiol column density of about 2 to the 13 centimeters to the -2. And finally, we tried to imagine the chemical network in which interstellar ethendiol can be placed. So the formation of this species in the interstellar medium has never been investigated to date, mainly because these molecules were not detected so far. So we don't know whether these species might be formed efficiently in the gas phase or on grain surfaces. But several routes can be hypothesized in any way. So like the reaction between the OH radical and vinyl alcohol, or the isomerization of glyceraldehyde, the hydrogenation of glyoxal, or the reaction between several different one carbon atom units. However, most of these routes clearly show some problems because, for example, the isomerization is very unlikely at low temperature, and the availability of hydroxymethyl or hydroxymethylene radicals is unknown at present, so we cannot speculate too much on this route. But even if we cannot yet draw important conclusion about the origin of ethendiol, we can confirm that this molecule is there, and still we can imagine that this species can act as a precursor of the most simple sugar, that is glyceraldehyde, which has already been found in meteorites, but not in the gas phase of the ISM. So that would be the next ideal target for astronomical search. So in conclusion, we have had a thesis in the complex puzzle of the C2H4O2 isomeric family. By recording and detecting the new molecule, so which is 1,2-ethendiol. So the last missing pieces would be now 1,1-ethendiol, which is most likely detectable in the interstellar medium as well. And the derived molecular abundance ratio toward this source show that 1,2-ethendiol is about 5 times less abundant than its tautomer glyceraldehyde, and this is in agreement with the fact that it's less stable, and is also 7 times less abundant than its possible precursor vinyl alcohol. And we also note that ethendiol is at least 2 times more abundant than the more complex glyceraldehyde. So in this context, of course, future studies will be a great step towards the comprehension of the chemistry of 1,2-ethendiol in the interstellar medium, and both theoretical, spectroscopic, and observational study can help to reveal or to gain more insight about this species, and for example, by clarifying the reaction mechanism that lead to its formation and to its transformation. So I'm concluding here. So I would like to acknowledge all the people that collaborated to this project, as well as the people with who I worked during the past years. And of course, I would like to thank you all for your attention.
Thank you for a very nice talk. So we have one question in the chat to start, which is, they say they haven't done any observational studies. So they're wondering how you can confirm that the fits to the observed spectrum are the molecule of interest, because it looks like there's some overlap with many features in the fit areas.
Yes. I didn't write all the overlaps here. So some molecules that are blended to our blind emission are, for example, thioformic acid. So I think most of, there is only maybe one unidentified features in the top right panel. So, but since this source is quite studied. Many molecules have been identified so far in this source. I think it's more than 140 or something like that. So most of the line that interfere can be excluded because they are already assigned to other molecules. But I think what makes this detection robust is that under LT condition, all the lines match pretty well what we expect to see, and there is no missing lines. Basically, this is, I think, is the strongest point that supports this detection. Yes, under LT condition, no line that is predicted to be above the noise level is missing. So all of them are there. So I think this is pretty convincing.
How many lines is it? It looks like quite a few.
It's like 9 pairs, because with the line width that we have in this source, we cannot resolve the tiny splitting due to the inversion. So in principle, they should be 18 lines, but they simply overlap. And this is somehow an advantage because they sum in intensity. So the total integrated intensity of each line is higher than a single line. But I think 9 pairs is convincing.
Are there any additional questions before we move on? Okay, well, thank you very much. I appreciate your presentation. If you could stop sharing your screen, and then
yes.
Dr. Orlando, if you could share your screen. So Dr. Tom Orlando was a chief scientist at PNNL before joining the faculty at Georgia Tech in the School of Chemistry and Biochemistry and the School of Physics, and he's a full professor there. He is also past chair of the Department of Chemistry and Biochemistry, and he was Associate Dean of Research for a while. In addition to running his own photo-induced chemistry on surfaces, or EPICS lab, he's the co-founder and past director of the Georgia Tech Center for Space Technology and Research, or CSTAR. And he's PI of NASA's REVEALS Institute, which studies radiation effects on volatiles and exploration of asteroids and lunar surfaces. In addition to his research, which is focusing on understanding non-thermal processes at surfaces and interfaces, he's also involved in programs dealing with radiation-induced damage of 2D metamaterials, complex biomolecules, carcinogenesis, and materials-based risk mitigation strategies, which are particularly with respect to sustained human space exploration. So thank you so much for joining us today, Tom, and please go ahead.
Great. Thank you very much, Heather, for the introduction, and Chris as well for the invitation. I'm going to switch gears a little bit and point out the beauty of doing a very high resolution spectroscopic study, such as the previous speaker, and point out that spectroscopy is an important component of the search for water on the moon, but the lack of resolution is a big issue. And it's part of the story that I want to tell. And it's specific to the lunar surface with respect to the talk, but much of what I'm going to say also applies to things that happen in star forming regions and with any body that's being irradiated by the solar wind in particular. So any body that has no atmosphere and can be radiated or irradiated. These processes will occur. So we'll specifically look at water on the lunar surface, how that happens, when it happens, and where. The work is primarily by Brant Jones, who's a senior research scientist in our group, and then by Alex Alexandrov, who's also a senior scientist in our group. And it's columnated by Darby Dyer and Carl Hibbets, who are both card-carrying planetary geologists. It looks like we're all the way to the end here. Okay, so let me put it in perspective. This is the time frame and sort of plan of NASA with respect to the Artemis program. So Heather mentioned that we are part of the survey network on the REVEAL Center, which stands for Radiation Effects on Exploration, Volatiles, and exploration of asteroids and lunar surfaces. Big emphasis on the lunar surface and the coupling to Artemis. The bottom line is there's multiple events that will occur as part of the Artemis program, Artemis 1, Artemis 2, but at the very end is Artemis 3, and that will have astronauts on the moon for an extended period of time. And therefore, there has to be a paradigm for sustainability. That underscores the importance of understanding where water is on the moon and whether or not it can be retrieved and utilized, because that's necessary to sustain the human presence on the moon. The time frame is going to shift. This is written to have people or astronauts there by 2024. The overall plan has not changed, but the time frame is still being defined. Okay, so here's what I want to point out, and I want to sort of back project to the previous speaker who gave a marvelous talk on the importance and beauty of high resolution spectroscopy. There's a lot of information, spectroscopic information in particular, for orbiter missions and flybys. And they indicate that there's probably water, or more correctly, hydroxyl on the moon surface. So these data sets come from the M-Cube spectrometer on the Chandrayaan 1 spacecraft, the VIMS spectrometer on the Cassini spacecraft, and the extended mission Deep Impact spacecraft. They all collectively yielded very compelling evidence for hydroxyl for sure, and water has a question mark there because we'll talk about why there's ambiguity. I think it's really clear if you look at the data from M-Cubed, which is on the left. This is from Jessica Sunshine's paper. If you look at the wavelength range, which is on the x-axis, you can see that there's an absorption right around 2.8 microns, or 2,800 nanometers. And then it stops right around 3 microns. And that's a cutoff, it's a technical cutoff with the spectrometer. The reality is, if you look at the spectroscopic observations of minerals that have been aqueous alterated, they have hydroxyl termination sites. That shows up in the same spectral region. If you look at water, it shifts a little bit towards the 3 micron. If you look at ice, it's a little bit past the 3 micron band. You cannot make an assignment with respect to the presence of hydroxyl versus water unless you have the full band profile. And so there's a lot of ambiguity as to how much of this is water and whether or not there's any water at all on most of the lunar surface. There's no ambiguity that there's water trapped in the permanently shadowed regions and on the poles. But there is ambiguity as to where the water came from and how much might be on the sunlit side. There's a number of reasons or sort of theories that have been put forward with respect to explaining how water got on the moon. And one is obvious, it's a geochemical sort of intrinsic process from volcanic eruptions. The water that was trapped in pyroclastic materials were sourced from deep in the interior. However, it's not really present in sufficient abundances to produce the spectral signatures that have been detected by the spacecraft. Delivery via comets, meteorites, and interplanetary dust particles. So that can make water and it could deliver water, but they also sort of garden and refresh the surface roughly every 80,000 years. So that's a little bit complicated. What I will focus on is the role of the solar wind in inducing or being involved in the production of water, and then get back to the importance of meteorites, but focus a little bit more on not the great big impact events, but more of the small, continuous small impact events correlated with micrometeorites. And I want to tell you right up front that the reality is we need solar wind implantation to hydroxylate the surface, implant hydrogen within the regolith, and then you need a transient heating, or you need a heating process to thermally induce the formation of water. So it's actually the synergistic interactions of both of these which are most important. Before we get into that, we ask a simple question, and that is, at what temperature can water actually stay on the lunar surface? which is from a surface science point of view, a very trivial question, and we were very surprised that this hadn't been addressed properly. So we put together a small ultra-high vacuum system to measure exactly that. What is the binding energy of water on lunar materials? And what is the binding energy distribution of water on lunar materials? Because you have all these different sites. It's not a really simple single crystal surface. And then what is the rate of removal? And then what is the rate of transport? Because these are going to be important numbers that we're going to need to have so that we can sort of model the behavior of water on the moon and deliver that information to the Viper mission in particular, which is going to be doing a reconnaissance mission very soon on the moon for water in particular. So this is an ultra high vacuum system. Base pressure is 10 to the minus 10 torr. And it's all set up to measure the release rate of an adsorbate, in particular water, from the surface of lunar materials. It has a liquid nitrogen cooled sample holder, which has a detachable cooling connection. That's actually fairly important because it allows us to cool the sample very well, very quickly, and control the temperature. But then we can detach it and do a temperature programmed desorption with very controlled filament heaters and be certain that the water that's leaving the particular sample is just coming from the sample and not the sample holder. Okay. We measure the release rate of the water using a quadruple mass spectrometer for mass resolve detection. The sample's on a gold-plated sample holder with a Type K thermocouple, and then what I already mentioned this, you can actually do the TPD and get a very nice spectra with a very little background subtraction, which is important. Okay. So this is an example of a temperature programmed desorption measurement of water leaving two different samples. I have a Highland sample on the left and a Mare sample on the right. It says desorption rate, but what we do is we measure the number density of water molecules that leave the surface as a function of the substrate temperature. We control the heating rate to within a few Kelvin per minute if we want. And then we measure the number density as a function of substrate temperature, and we sweep the temperature. We have a temperature ramp, and then we measure the rate of removal. If you look at the kinetic equations we use to analyze this data, and we can see how fast the water molecules leave the surface, and then from that we can fit and determine how strongly bound they are. The purple is the fit, and there's a dotted line that's in the middle of the purple run. And then you can see that purple run is a combination of minimum of two components. We call it a low temperature component and a high temperature component. So some stuff that comes off very early in around about 175 Kelvin, and then stuff that comes off at a much higher temperature around 250 and higher. This is important. We're looking at water chemisorption. We're not looking at ice. Okay, we're looking at the amount of water that sticks to the surface, not the amount of water that sticks to itself, which is ice. Okay, so one thing you should notice is that there's more water coming off of the Highland than is the Mare. And their profiles are generally the same. They both have a high temperature and low temperature feature, but they behave differently, and the Highland has more water. Okay, so how do we treat this data? Well, I already told you we basically look at and deconvolute this into both a high temperature and a low temperature feature. And we do this by fitting the low temperature feature to this double sigmoidal fit, which is shown in the red. And then you subtract that. And this is all done after we've done the background subtraction for anything that might be correlated with the substrate holder and the instrumentation itself. So we can get the low temperature feature, and then it leaves a residual high temperature feature. And then you can analyze these temporal profiles or the temperature profiles using standard Polanyi-Wigner kinetics. So we write down the simple Polanyi-Wigner equation. This is a very simple kinetic equation, which relates the removal rate to the activation energy. It's an exponential function of the activation energy over RT. This is extremely well known. There is a coverage dependence theta raised to the n, and n is the order of the desorption. So that's important. So ice desorbent is zero order. A chemisorption event where you have, desorption from a chemisorb state, that's first order. I'm going to tell you a lot about a process where n equals 2. N equals 2 is for recombinative desorption, so it's a second order process. And I'll show you that water is formed on these surfaces via a second order process, which is recombinative desorption of terminal hydroxyl groups. So you basically have terminal hydroxyl groups that can get together. If they're close enough, they can interact with one another, they form water, and they actually heal a defect that is on the surface. What's important here is actually you can recast the formalism for the activation energy in terms of a coverage dependence term. So you can extract from the data the coverage dependence of the activation energy. And you can then turn that into a probability function or a binding energy distribution function, which is necessary for the modeling activity. Okay, so that shows what it looks like for the Highland, and then we do something very similar for the Mare sample. And they're generally similar. The peak is a little bit above 50 kilojoules per mole, which is typical for ice. So the binding interaction with the substrate or the mineral or the regolith is a little bit stronger than with water itself. And then having said that, you have a distribution of sites that go out to 3 times the interaction strength, but there aren't that many, okay? A lot of that has to do with what the chemical compositions of these particular minerals are, or these particular samples are, and the relative amounts of metals. So I want to get to that, actually. This is pretty important. You can see this, the binding energy distribution for the Mare is narrower than it is for the Highland. Okay. So because the water has a binding energy, which is pretty close to that of ice, and a distribution that extends out to higher energies, but not that many sites, the reality is that water does not stick on the lunar surface over much of the lunar surface as a result of simple lunar heating or solar heating. So over a normal lunation, you'll get thermal desorption of the water over most of the latitudes, except for when it's very cold and very high up and near the poles, or in the permanently shadowed craters. So water doesn't really want to stick and stay around as the lunar surface heats up from its coldest point out to its hottest point, which is typically at the very hottest point or right in the sunlit region, not much more than 400 Kelvin. I'm not going to say a whole lot about this. We did a lot of work on this. In particular, Alice D. Simone wrote a thesis on this where she did photodesorption measurements of water from the lunar samples. And the photodesorption cross-section is also very high. So the thermal desorption cross-section, thermal desorption rates are high, and the photodesorption cross-section is high. So the bottom line is molecular water really shouldn't be the main signature for this 2.8 to 3 micron signal that's been observed by most of the observational flybys, the M-cube spectrometer, and so forth. Okay, so our contention is it's primarily due to OH, which is produced from proton irradiation. And then at the very end, I'm going to get to it, and it can be trapped water, but it's not chemisorb water, and it's different. Trapped water is ingrained and encased within the regolith itself. Okay. So this is probably the most important slide of the entire talk. I'll spend a little bit of time on it. So this is the scheme of what happens when the solar wind irradiates the sample. The solar wind in particular has energetic protons. Their energies are typically around 0.5 keV on up to 1 keV. They embed themselves into the lunar surface. And when I say lunar surface, we're looking at this with respect to the moon, but this can also happen on asteroids and interstellar grains and anything that is being irradiated by the solar wind. They have a limited penetration depth, primarily based on the Bragg stopping distance, which is dominated by a DEDX term, which is electronic excitation. And they embed themselves, in 50 nanometers, maybe all the way up to 100 nanometers depth. So there's a sort of this rim of proton buildup. That's dependent upon the proton flux, of course, which will be dependent upon the latitude. But their implantation is largely, since it's a DEDX term, this is a temperature independent process. So after it's proton irradiated, what you have is very stable metal hydroxyl termination sites, and then some metal hydrides. If the hydrogen isn't taken up as a metal hydroxide or a metal hydride, the interstitial hydrogens don't trap very well, and they recombine and form molecular hydrogen, and that's lost. And so there's always this sort of release rate of hydrogen from the moon because all of it isn't trapped. And the MOH and the MH, they're very stable in these minerals and glasses, so they build up over time. Okay. These build up, and in our opinion, the MOH in particular is the bulk of the optical signature that is seen by this spacecraft. Okay, now there is something in the spacecraft data which is interesting. There's a latitude and temperature dependence. So there is a subtle modulation in the spectroscopic signature, potentially on a diurnal basis, certainly on a latitude basis. So the question is, what is that from? Okay, so what I'd like to show you is that you can modulate the amount of OH that is seen in these optical reflection measurements by paying attention to the fact that you can have these move or diffuse within the material. And it moves by a proton hopping mechanism. The mass isn't the oxygen moving around, but you have a proton hopping from one site to the next until you get to the surface where you have a large amount of hydroxyls that are terminating at the surface and on the grain boundary edges. These can then meet one another, form water, and that'll leave. But it doesn't escape the moon because it doesn't have an escape velocity which beats the Jeans escape. It just bounces around, and it might hit the moon again and stick or dissociatively absorb, but eventually it can make it to the polar caps and the polar permanently shadowed regions. And in so doing, there is this temperature dependent depletion signal of the OH. Okay, so that's the story. We're going to stick to the story, and we're going to show you how we have a model that is pretty commensurate with the mission observations as well as the lab observations. So this is the first step. So it's well known that if you irradiate these minerals or the lunar materials, you can implant this proton, like I said, to a depth, 30 to 50 nanometers. And then this is a nice spectra of the 2.8 micron feature when protons were irradiating olivine to a saturation number density of about 10 to the 7 per cubic centimeter. And you can see, this is an absorption. I was showing you reflection measurements, but you can invert this. You get a very broad feature, which is reminiscent of what was seen in the M-cube reflection data. That was for olivine. If you do this for amorphous silicate or a glass, you get something quite similar. If you irradiate these materials with a helium ion, you don't get it, and that's because the optical signature of this is the metal the terminal hydroxyl sites. Okay, so here's an interesting chemically related issue. If I have these terminal hydroxyl sites and I heat them up, I told you they can react with one another and make water. Well, that's well known, and this has been well studied for glass. And so this shows you, they're measuring the SiOH SI ratio. So they're mapping the SiOH number density optically for fused silica and carbazole, which is a type of glass. And they can see that the SiOH sites or numbers drop off with temperature, and that's because you have this dehydroxylation and recombinant desorption going on. It happens at a pretty high temperature, and you have two regions. You have one that's shown by the blue line, and one that's shown by the red line. The one that's the blue line is a little bit easier. These are a little bit closer to one another. These are geminal sites. And then you have vicinal sites, which are a little bit further away, and it takes a little bit more energy. The important point is that this is a high temperature for glass, right? Just plain silicon oxide. But if I change the silicon and I add aluminum, magnesium, calcium, iron, titanium, and in particular magnesium, iron, and titanium, this shifts the temperature down considerably to the point where you can have recombinant desorption at temperatures as low as 250 Kelvin. That's within the temperature range that the lunar surface cycles over. So that means that the lunar material can have this going on at much lower temperatures. That's important. So we did these measurements with actual breccia and basalt lunar samples. This is the composition of the oxides that have been measured, and they're in the lunar compendium. And then we did some modeling with what we would call our lunar recipe, which has 15% TiO2 and 15% magnesium oxide, and the rest silicates or an aluminum silicate. And we paid attention to the overall importance of recombinant desorption. So let me remind you what recombinant desorption is. You take a look at the right-hand side, I've got these two hydroxyl groups just sitting there, and I can get them to sort of move around and activate them to meet each other and form water. And when that happens, the water leaves and I can heal an oxygen vacancy. Okay, the data we got is for sample 1084, that's I think a Mare sample. This is a TPD spectrum, but it's over a much longer and larger temperature range. So the blue feature is what I kind of showed you already, but we went on out to all the way to the point where we got to 1250 degrees or 1300 degrees Kelvin. You can see three features, right? So the first one is what I've told you about. The second one is subsurface processes or things that are happening in voids. And then the third one is something that happens at much higher temperatures, and you get sintering and eventually melt. All of this happens when I have an impact event. So you have a regime of temperatures where you're making water over three different sort of spatial regimes within the material. So I'm going to speed up because I want to get to the crux of the matter here. We have a full kinetic model for this, of which most all of these rates have been either measured by others or measured by ourselves. And so we put this in where we have the proton implantation, we build up the OH, we let it photodesorb, we let it thermally desorb, and we let recombinant desorption go on, and that makes water, and then that water can leave. We look at the photodissociation of that water, whether or not we have anything that comes back. And then eventually what we do is we keep track of how much water is made, where does it go, how long does it stay in the exosphere, and where does it land? So it's a very comprehensive model. The first shot of this is on the left. You start out looking at the very beginning at local lunar time. So this is time versus latitude. And time actually is also temperature because the temperature changes during lunation. So in the red zone, I start to get a little bit of water formation only at the low latitudes. And then I slowly get some building up at the higher latitudes. If I let this go for 3,600 days, you can see that this continues to go on. And what it does is it causes there to be water formation at the low latitudes, but then it builds up and moves up and populates the upper latitudes. So that's better seen here, where in the middle frame is the one I just showed you. You're having water formation thermally by heating up the OH that's in the hot zones. And then eventually this stuff sort of moves on up towards the poles. And so you get depletion regions in the hot zones and buildup regions in the cold zones. And so you can see this clearly in a sort of rectilinear coordinates in frame C. Okay, so anyway, it maps out very well with the data from M cubed, which is on the left. The observation data is digitized and it's in these solid squares. And then our model is the blue. It doesn't match it at the top because of the truncation issue with the and the time we need to capture what's happening directly at the poles. But overall, the match is very good. Okay, so our bottom line is the OH is, and I already said this, the sort of diurnal changes that are being shown that I just showed you from the M-cube data can be matched very well by stimulated changes in the OH number density. And then that forms water, and these are transported, and then they end up actually making water that ends up on the poles. Now that simulation was just for the lunation temperature, but I want to point out that when I have a micrometeorite spike, I can get all of the states and all of these temperature regions forming water. So a significant fraction of water is actually made by impacting proton embedded saturated regolith. That'll produce water. And there's actually the Laddie observation confirms this. Okay, another confirmation, which I really want to spend a little bit of time on, and then I'll finish, is a collaboration we had with Casey Hannibal and Paul Lucy, where we actually did spectroscopy above the cloud layer. And we did this using SOFIA. So we flew above the cloud layer and we pointed the spectrometer onto the moon, and we mapped out the 6 micron feature on the moon. And lo and behold, we were able to see a very clear 6 micron feature in an area which is actually in a latitude where there shouldn't be water. From a thermal perspective and a photodesorption perspective, there should be no water. Yet we saw it, and it was a reasonable amount. In fact, if you looked at the line strengths, it estimated an abundance of 100 to 400 micrograms per gram of water. That's a significant amount if you're up there searching for water. And it's particularly interesting because it's not where it is indicated on this cartoon. It's much closer to the equator, right? In a region where it cannot stick. So the idea that we put forward in this paper is that it is made by these impact events. And there's some water trapped during the vitrification process. And maybe a lot of the water that's been seen by the spectrometers is trapped water, which is important to know because it's not easy to get, and it won't be that amenable to any kind of resource or in situ resource utilization strategy. If you need to go and get the water, you pretty much have to be in the polar, permanently shadowed regions or the icy regions where you may have chemisorb water or ice layers. So on that, I'm going to summarize and point out that the binding energy of water has been measured pretty well for Highland and Mare samples. They're 60 and 65 kilojoules on average, respectively, slightly higher than water on itself. The Mare sample binds more water than the Mare. That's actually commensurate with the observational data. I guess this is the important thing. Water can be formed in situ by thermally induced reactions. The solar wind produced hydroxyls by recombinant desorption. This is something well known in surface science, but it's certainly not well known in planetary surface science. If you incorporate this into a model, you can basically reproduce the observational data quite well. I do think that micrometeorite delivery is probably the primary source term for water on the moon, and we've looked at that and have some very nice SOFIA data to sort of back up that supposition. And I don't have time to talk about this at all, but this happens on Mercury as well. And in fact, our model shows that Mercury has more water on the poles from this process than the moon. And on that, I'm going to stop and leave it open for discussion. So thank you very much. And I should have stopped a little earlier, but there's still time for some discussion.
Yeah, thank you, Tom. So there's a couple of questions in the Q&A. One of them I think you already addressed a little bit. So the second question is, if hydroxyl radicals form, does hydrogen peroxide also form?
Right, so that's a good question. So the recombinant desorption step itself is going through a hydrogen peroxide intermediate. Okay, so the two OH groups sort of meet one another. They make a hydrogen peroxide intermediate, but that is not stable. So what happens is one of the oxygen basically takes both of the hydrogen, it leaves as a water molecule, and it leaves behind an oxygen in the bridging site where between the metals. So I end up with a metal oxygen metal bond. So there is hydrogen peroxide sort of involved, but it's not a stable product.
The other question was, water evaporates from Earth every day. What is the mechanism for that evaporation? And does any of that go to the moon?
Okay, so water does evaporate on the same way from Earth as it is on the moon surface. You need to have this thermally activated thermal desorption, right? And then it'll leave. And then what it'll leave with is a sort of a translational temperature, which would be thermally equilibrated to KT. And it doesn't have to be that hot. So it will not make it to the moon because it has no real escape velocity, and we have a heavy atmosphere. So it ends up in our atmosphere, and then it goes through an entirely complicated water cycle. There is in the planetary science community what we are calling a water cycle, but it's nothing like the water cycle on Earth, right? You know, the water cycle there is you make it, it gets into the exosphere, it has these very large excursions and comes back, and it hits the moon and probably breaks. Then it has to form again, and then finally it gets back and maybe hits a cold spot and sticks. But the way it desorbs from Earth is, Earth materials is basically the same on the moon, except for there's nothing to stop it from going up to the poles.
Are there any final questions before we take that? Okay, well, I would like to thank both of our speakers. Thank you so much, Dr. Orlando, for your presentation, and thank you, Dr. Melosso, for your contributed talk earlier. And we will be sending out announcements soon about our summer AstroCheminars and also about our dissertation award. So please keep an eye out for that. Thanks you all for joining us today. Have a good afternoon.
Thank you for organizing this. Bye-bye.